Then we have the next example of functions, quadratic functions. But also called second degree polynomials. When that is a function, you can write in this way. So you have one part looking the same as this is just a linear function. Instead of k we call b, and instead of m we call c. So if I add also a term with x squared, then I get the quadratic function. So a linear function you can have as a special case. If you put a equal to 0, you will get a linear function. But we will now look at examples where this is included, otherwise it's silly to call it quadratic function. So where can you come across this in real life? Yeah, for example, if you, as we have seen before, if you have a person throwing up a rock into the air, then the height, how high above the ground the ball is at some certain time, x. So the height, y, as a function of the time, how long time has passed since you've thrown it, x. That will be given by a second degree function. And there are more examples. So there are a real life example of this. And there's also a good way to train on functions a little bit more difficult than linear functions. Okay, so let's see first some general concepts having to do with quadratic functions. So if I now want to draw a quadratic function in the graph of that, then I need to make a table as usual. Then I need to pick some points here, look at the corresponding y's, put them in here to my coordinate system, and then I need to draw, see how it looks. But since that will be a little bit sloppy to draw freehand here, let's switch to GeoGebra and look how it looks there instead. Because this is nothing new now. For every time we want to plot a curve, we just make a table and put the points in. So that's not so interesting here. So let's look at the end result instead of looking at different functions here. So let us take some examples here of curves. For example, if I have, just take some arbitrary, 3x squared plus plus 4x plus 1. For example, like this. Then we see the graph shown here. Or if we take another one, minus x squared plus 3x plus, we could take minus here, plus 5 or 4. Then we see we get this one. Then you see no matter what I draw here now, so no matter what I put in here now, if I put in a quadratic function, I will always get a curve of these two types of shapes, either a curve like this or a curve like that. Then these could be different widths here, and the peak here could be at different heights. It could be moved to right and left and up and down. But the general shape of the curve is either this one or this one. So these are the general appearances of quadratic functions. So let's see what is the most simple one we can find. It is x squared. That's the most simple example of a quadratic function. And we see it just simply look like this. So if x is 0, then y is 0, x is 1, y is 1, x is 2, y is 4, since it takes the square of every number. Okay, what happens if we change this a little bit? For example, if you take 3x squared, then we see that we give are given the same shape of the curve, but it's a little bit steeper. So this curve is a little bit steeper. And if we instead, for example, take a half, then we'll get less steep. Same shape, but less steep, this pink here. Then we could also switch, for example, take minus x squared. Then we see that we get a curve down here instead. So this is just a mirror image of the blue one in the horizontal axis, since every point now is just minus. And for example, if we take minus 3x squared, we get this brown one here, and this is just the mirror image of the orange one. Since these two, the only difference is that they have a minus in front of one, then they become below the x-axis. So in this way we can draw the most simpler cases. What happens if I, for example, write this? So if I write this example, x minus 1 squared. Then I see I get this green curve here instead. Comparing it to the blue one this is x squared. Then x minus 1 in parentheses squared. Then it has moved one step to the right. Otherwise, these two curves are identical, but the green one has moved one step to the right. So putting a minus 1 here has the effect of moving the curve one step to the right. So if I instead, for example, then take x plus 1, then you see I get a red curve. So this has the effect of moving it one step to the left. So if I add 1 here, it's the effect of moving the curve one step to the left. And if I take x plus 2, then of course we can guess what will happen. The whole thing will move 2 steps to the left. Okay, so that is the effect of that. And for example, if I now do this, what happened then? So now if I take 3 times x minus 1 squared minus 1, if we start with the x2, that's this one, blue, then we moved it one step to the right by putting a minus 1 here inside. You got the green one. Now in front of that I multiplied with the 3 and I took away minus 1. Then we see it had the effect of minus 1 had the effect of moving it down one step. And the 3 here had the effect of making it more steep compared to the green and blue one. So all these work independently. So you see the number here inside moved the whole curve to the left and right. This number makes it more steep or flat, or also could invert it here, like mirror image. This number here moves the curve up and down a number of steps, in this case 1 step down since it's negative. So if you have a function of this form, then we can easily figure out how the curve will look like. And now we will show that every quadratic function can always be written in this type of form, meaning that all quadratic functions will always look like something like the orange here. They have moved to the right, left, up and down, and become more or less steep. But it could also, of course, be negative here. So if I put a negative here, they will have the orange one, but inverted. So now we will show that we can always write in this form, meaning that all of these quadratic functions will always look something like this, or inverted like that. Okay, so we take our example here now that we had this one, for example. It's easy to show that this is an example of quadratic function. If we use the rule here for squaring a difference, then we should take the first one squared minus a double product 2 times x times 1 plus 1 squared. So this is just this one, and then minus 1. And if we multiply in the 3, we get this. And if we simplify, so you see that this one is an example of a quadratic function, because here is a quadratic function. So if you have a function of this form, that means it is a quadratic function. But can we do the opposite? If we have a quadratic function, that is, if we have a function like this, can we always write it in this form? That is, can we always write it in this form? Here now a, b, and c, the larger one, are also constants, but not necessarily equal to the smaller a, b, and c. So the question is, if you have like this, can we always write it like this? Can we re-express it like this? And the answer is yes, we can. So that's what we want to show now by training on how to transform if you have like this to this. And what's the point of that? Yeah, as we have seen, the point of that is that by doing this, we saw in when we draw our curves, that we easily figure out how the curve looks like. Because this moving to the left and right, this is moving up and down, and this making it less or more steep or inverted. So it's not so easy to say how the curve looks from this, but it's easier to say from this. And also doing in this way will help us when we're solving equations. When we finally will put this equal to 0, this will be easier to solve than having it in this form. So there are several advantages of being able to write it in this way instead. So now we will show that it can always be done and how you do it. Yeah, the trick of being able to show that is to use the two rules we have seen for squaring a sum and a difference. We had the rules for squaring a sum and a difference was this. And these are the ones we want to use now when we're writing. Because if you look at the right hand side, our quadratic function looks something like this. And we want to rewrite it in something that looks like this, more or less. So we want to go in this direction. We will start with something that looks like this and go in that direction. But to be able to do that, we must have a lot of practice with doing this first. So let's just look at some examples first. For example, if I have x plus 1 squared, then the first rule here gives us that this is x squared. 2x times 1, that's x. And then 1 squared. Or for example, x minus 3. This is x squared minus double of this, 6x, and 3 squared, that's 9. So we need to be sure of these rules now, how those work, because going in this direction is the simple way. But now we want to start in this form and write it in this form instead. And to be able to do that, we must be sure of going in the other direction first, otherwise it will be tricky. So let's start out with some simple examples and then gradually make it more general. So let's take the following example. Let's start with this one. Can we write that in the form of this? Now we want to write everything in the form of this. That is, we want to write it as a parenthesis square, because the advantage is now that here we have x in 2 places, but here we only have x in 1 place. So this is easier to work with. Here it's very easy, because this is just directly we can identify it's x plus 5 squared. And how did I see that? I saw that it's x squared, so I can suspect that I can use this rule. And this is just 5 squared. And this works because it's double the product, 10 here. So I can see directly this is just doing this step, doing this square over sum backwards. But what would happen instead if it would have been like this? Now we see that it doesn't work anymore for square of 5 here. But this is easily solved, because if we write it like this, we see that this part here now we can write as x plus 5 squared, and this one just follows along, and this here is in this form. So now we know how to write this in this form, even if this doesn't go up to a square as we would like. Okay, so that's one way. Let's take quickly one more example. Let's take if I have 4x plus 1. How would we do that? Yeah, if we would have 4 here instead, it would be simple. It would be x minus 2 squared. This will be the same. But now we don't have 4 here. We had 1. So if we write this out here now, this will be x squared minus 4x plus 2 squared, 4. So you say it doesn't match directly. But we got 4 here, but we wanted only 1. But if we just subtract 3 on this side, now it works. Because now this is this, and we subtract 3 from that, this will become 1. So now we have equality for these two sides. So I can work like this. Okay, so this is how I do it if the constant doesn't match. So let's take another example. Let's see what we would do if it looks like, for example, this. Now it's not obvious what to do here, because it's not equal to 1 squared, for example, because x squared and then y squared, but it doesn't work for this one. This doesn't really work. And so what should we put here instead of 1? We see that when we make this one and square it, this one will be multiplied by that and by 2. So you have the double product. That should end up like this. So that one times 2 should end up like this. That means that what should be written here is half of that one. If you put 3 halves there, then it should work better. Because what do we get now? We get x squared plus double of this, and then the 2 disappears, and we get 3x. So now we're happy because this corresponds here. But instead we got problem now with this one, because now we got 3 halves squared. And 3 halves squared we don't have on this side. What is 3 halves squared? It's 9/4. And 9/4 we don't have on this side. We have 1. But if we take away 9/4 here, then this will disappear. And then we can just add up 1 at the end. So now everything will work out perfectly. So let's show that it does. Okay, so how will this be? It will be x squared. Double of this is 3x. And then this squared, we saw that was 9/4. But now we have minus 9/4. And that will take out that. And this plus 1. And now we will see that this is exactly what we started with. So this here is the way to go. So you can write it like this. The only thing we have to do now is to simplify this here at the end. So all we have to simplify now is this at the end. We should write as 1 constant, not 2. This minus 9/4 plus 4/4. So this is x plus 3 halves minus 5/4. And now we have it in this form, ax plus b. You see here a is equal to 1, b is equal to 3/2, c is equal to minus 5/4. So now we have it in this form. And for example, if we wanted to draw this now, it will be simple. This is not so easy to see how the graph looks, but here it's easy, because it's just to start with the x2, then we move it 3/2 step to the left. This means moving it 3/2 step to the left, and then 5/4 steps down. So from this, starting with this and just manipulating this stepwise, we could figure out how the curve looks like. So that's the advantage of having it like this. And also we will see that it's easy to have like this when we want to solve equations. And let's take a final example. So what do we do if we have something like this? 2x plus, or 2x squared plus 2x plus 1. It doesn't get much more general than this. Of course we can have minus here or something. Now the difference is that we don't have 1 in front of the x squared. So what can we do then? And the first thing we can do, we can factorize out the thing in front of the x squared. And then we get this. Because now we have this in the form we know how to work with. So now if we transform this, then it will work out. So let's do that now in the parentheses. Here we can start to write it like, okay, it must be x plus, since it's plus there, and square. What should we put here? Yeah, the double product here should give a 1. So here must be a 1/2. Since this times 2 gives this one. But then we also get 1/2 squared. And what is 1/2 squared? Yeah, that's 1/4. And we won't want a 4th, so let's take away this. So now, what have we done? Yeah, if we take the square here of this one, we will get x squared plus double product here, we get x, and this square we get the 4th. And then we take away the 4th, so this cancel. So now we are left with this part. So this part here is the same as this one, and that's same as this part. So the only thing we're missing now is a 1/2. Okay, so how do we continue? Yeah, let's start simplifying what's inside the parentheses. Minus 4th plus a 1/2, that is plus a 4th, using normal fractional computations. And now we only have to multiply in this again. And 2 times a 4th is a 1/2. And now we finish, because now we have written this. We have re-expressed it as this. And this is in the form of ax b squared plus c. This is in this form. So this is just, this was a sloppy plus. So this is just moving the curve, x2 curve, x squared curve, 1/2 step to the left, 1/2 step up, and then making it twice as steep. So that's how you could sketch that one. So now we know how to do any quadratic function. We always know how to do it into this form. So now we have in practice basically shown that no matter what this is, we can always write it in this form. And when we come to quadratic equations, second degree equations, then we will see that having it in this form instead of in this form, then it makes it much more simple to solve the equation. but more about that later.